In the previous video, we modeled the situation described here where a rectangular swimming pool was surrounded by a walkway of uniform width, and we're asked to find the width of that walkway. This is the equation that we developed in the last video, and now we're going to take a moment to solve for x. We're going to first distribute the product of the two binomials that we see here. We'll get 28 times 22 is 616. 28 times 2x is 56x. 2x times 42 is 44x. And 2x times 2x is 4x squared. From that, we're going to subtract 22 times 28, which is 616. And now we're going to clean up the left-hand side of this equation by combining like terms. First, we see that 616 minus 616 is 0. We only have one square term, which is the 4x squared term. Then we have 56x and 44x that can be combined. Together, they add up to 100x. And we're going to set that equal to 216. Now, this is a quadratic equation. Let's go ahead and write it in standard form by subtracting 216 from both sides. So we have 4x squared plus 100x minus 216 equals 0. One of the things that I notice here is that we can simplify this equation by dividing by 4. 4, 100, and 216 are all multiples of 4. So if we divide by 4, as long as we do so in both sides, we will have an equivalent equation. So we'll get x squared plus 25x minus 54 equals 0. This is going to be a lot easier for us to factor. X squared plus 25x minus 54 factors as x plus 27 times x minus 2. Using the zero product property, it must be that one of these two binomials is equal to 0 itself. Either x plus 27 is 0 or x minus 2 is 0, which gives us two solutions to the quadratic equation. Either x is negative 27 or x is equal to positive 2. It's at this point that we have to revisit the original problem to see if either one of these solutions makes sense. Maybe they both do, maybe neither one does. Because we're talking about the width of a walkway in terms of feet, it doesn't make sense for x to be a negative number like negative 27. So in this case, there's only one solution that makes sense in the original problem, and that is that x is equal to 2. So the walkway has a width equal to 2 feet. Let's look at one more example for an application of a quadratic equation. This one is rather involved, so make sure that you have plenty of space to write down the work. We're told that a boat traveled downstream a distance of 80 miles and then came right back. That means it traveled another 80 miles on the return trip. If the speed of the current was 9 miles per hour, so that means that the water itself was traveling in one direction at 9 miles per hour, and the total trip took 6 hours and 40 minutes, we need to find the average speed of the boat relative to the water. I always like to draw whenever possible, so I'm going to be a little extra, and I'm going to draw the current as waves here. So when the boat is traveling in the direction of the current, we can say that its speed is the rate of the boat plus another 9 miles per hour. On the other hand, when the boat is going against the current, it's being slowed down by the current. And so the speed is the speed of the boat minus 9 miles per hour because the current is kind of pushing back on the boat. Now we know that there are two trips to and from, and that they were each 80 miles. So we'll say here that it was 80 miles to go in one direction and then another 80 miles to return. Let's put this information into a table similar to what we did in a previous section. We have a column for distance, a column for rate, and a column for time. And then we have one trip in one direction and then the return trip in the opposite direction. So we'll have that distance is equal to rate multiplied by time. One direction had a rate of r plus 9. The other had a rate of r minus 9. And both times, the distance was exactly 80 miles. What we don't know is the time that each leg of the trip took. But because distance is equal to rate multiplied by time, which we can write as d is equal to r times t, then by dividing both sides by r, we find that we can write t as being equal to d divided by r. In other words, time is equal to distance divided by rate. That's what we're going to use here in this third column. Time can be written as distance divided by rate. And we'll do the same for both legs of the trip. Now we do have one additional clue about the total time. The total time for the two trips was 6 hours and 40 minutes. Let's write this in a little bit of a cleaner way. 6 hours and 40 minutes can be written as 6 hours and 40 out of 60 minutes. And if we reduce this, we have 6 and 2/3 of an hour. And if we write this as an improper fraction, 6 times 3 is 18, plus 2 would be 20. So we can write this as 20/3 of an hour. That is the total time it took for both trips combined. And I think we can come to an equation that models the situation by using this third column. The time that it took for the first leg of the trip plus the time that it took for the second leg of the trip together equals 20/3 hours, which is the 6 hours and 40 minutes. I'm pretty convinced that we have modeled this scenario correctly, but for the sake of space, I'm going to solve this equation on a separate video.